Depending to the problem, we are going to choose different coordinates, xy coordinate, normal tangential, or polar coordinate, and use Newton equation in those coordinates to solve our problems. For example, I'm going to start with the simplest possible example, problem 1 in chapter 3. Here we have a box, 50 kilogram, so the mass is 50, which is moving with the initial velocity of, or we are releasing it with the initial velocity of 6 meters per second to the right. And there is a friction force between the box and ground. And that's going to be the only force that we have between the, in the x direction. And we want to know how long it's going to take for this box to stop after releasing it, and how long it's going to move before stopping. So this is a very standard and also very simple problem. So how we should solve this type of problems? We always need to start with free body diagram. We need to show all the forces that we have on our body. So I'm going to draw very simple schematic of the box and show all the forces that we have on it. Of course, we are going to have gravitational force on this box, a normal force from the ground, let's call it N, and also the friction force. The friction force is going to be to the left in this problem. And that's all. These are the only forces that we have on this box. We have nothing else. So this box is going to start with the velocity of 6 meters per second, and because of the friction, it's going to gradually slow down, and finally it's going to stop at this point. Our target, our goal is finding the time here and also the displacement. If this displacement from here to here, if I call it d, the question is what is t and what is d. Now is the time to choose our coordinate. So for this problem, because the box is just moving in one direction, probably the easiest coordinate is xy coordinate. So we need to show our coordinate always. This is the coordinate that I'm going to use here. And now we can use Newton equation in different directions, in x and y direction, to solve our problem. I don't know what is the friction force, and I don't know what is the normal force from the beginning, but I can find them using Newton equation. Sum of the forces in the y direction is equal to mass times acceleration in the y direction. But there is no acceleration in the y direction, so it's going to be equal to 0. In the y direction, we have normal force and mg downward in the negative direction is equal to 0. And from here, we can say normal force is equal to mg. And because this box is sliding, the friction force is going to be equal to mu k times n. So the friction force is going to be equal to mg times mu k, which is given. Now, I don't know what is the acceleration of this box, but I can use Newton equation to find the acceleration of it. Sum of the forces in the x direction is equal to mass of it times acceleration in the x direction. Let's call it ax. In the x direction, we have only one force, F, which is in the negative direction. So negative F, or negative mu k times mg, is going to be equal to mass times acceleration in the x direction. M is going to cancel out, and acceleration in the x direction is going to be negative mu k times g. As you see, I'm not putting any numbers, and you try to do the same thing. Don't put the numbers, the value of the mass, or g or mu k, anything. As far as you can just do it using just the parameters without putting any numbers to it. And also, this has a reason behind it, because if you do it this way, it's going to be much easier for you to catch your mistakes. And also, you can see something that if you put the numbers, you are not going to be able to see it. For example, here, look at A. We found A to be equal to mu k times g. It means the acceleration is independent from the mass, right? That's interesting. But if I put the numbers from the beginning, I'm not going to be able to see it here because I'm going to find just acceleration to be a number, right? And that doesn't show anything. So this is the acceleration, and also acceleration is constant. It's not changing at any time from here to here. So we are going to have a constant acceleration movement from here to here on a line. So I'm going to be allowed to use all of those three algebraic equations to solve this problem. For example, to find the time, I know the velocity at this point is equal to 0, and I know velocity minus initial velocity is equal to acceleration times t, or velocity is equal to v0. Let's write it this way: velocity is equal to v0 plus acceleration times t. I know v is 0, v naught is given, and acceleration we got it, so we can find time from here. Based on this, t is going to be equal to negative v naught divided by ax, which is going to be equal to, negative is going to cancel out. We're going to have v0 divided by mu k times g. Now we can put the numbers, and if you put the numbers, you're going to see t is equal to 1.529 seconds. After finding time, now we can find d. You're allowed to use any equation you want here. For example, you can use time independence equation. Based on that equation, velocity squared minus initial velocity squared is equal to 2 times acceleration times displacement, which is d. So v is equal to 0 and v naught is given. So d is going to be equal to negative v naught squared divided by 2 ax. And if I replace ax with negative mu k times g, d is going to be equal to v0 squared divided by 2 mu k times g. And now we can put the numbers. And if you put the numbers, displacement is going to be 4.59 meter.